lower level function, the lower level kind of wire function of a device where we have interfaces and we have caches that allow us to switch data from one interface to the other. So things like all of my layer 2 functions, ARP and being able to discover MAC addresses of neighbors or MAC addresses of devices that I'm going to be communicating with, those are all data plane functions. We do fast switching or we do Cisco Express forwarding at that data plane to ensure that data moves across the data plane as quickly as possible. The goal is to ensure that we're getting data in and out of the device as quickly as possible. The control plane in a Cisco iOS device are the brains of the device. That's the higher level functions of the device. Our routing protocols function at this layer. If we're doing packet inspection, policy-based routing, anything that involves processing the data through some algorithm or processing the data through some sort of function within the platform goes up to the control plane. And then the third plane of existence is our management plane. The management plane is the plane that allows us to perform things like SNMP, SSH, Telnet, and HTTP access to our device. Because the control plane is really the brains of the device, it's very, very important that we actually secure access to that control plane, not only from access control, from an access control perspective, by ensuring that protocols that are utilizing this control plane have authentication and whatnot. We also want to ensure that we're protecting against denial of service attacks against this control plane. The hardware and software that supports routing, that supports management occurs at the control plane, like we said. RFC 6192 talks about the need to protect the control plane from malicious traffic. All right? Anything that's CPU intensive, anything that is required for the router to make routing decisions is going to happen at the control plane. Naturally, that means if the control plane is compromised, the device essentially becomes useless, or at least severely degraded in its performance. Right? As this is a visual representation of what I was just talking about. The data plane is really a forwarding plane. It allows us to take data into one interface and send it out of another interface. Every once in a while, though, well, not every once in a while, quite often, there is some data that has to be sent up to this control plane and then sent back to the data plane for processing. All right? Think of, from a router perspective, all your routing protocols. BGP, OSPF, EIGRP, they're all going to have critical control plane functions that provide, well, really the intelligence that the router needs to be able to make decisions. So there are two ways that we can protect access to the control plane. Now, we don't get into it in a lot of detail in this chapter. We're kind of introducing these concepts. And then when you get into some of the higher level courses, you really learn about the specifics about protecting access to this particular control plane. But we have two options that are available with us. One is control plane policing, and the other one is control plane protection. We'll talk about the differences between these two in this slide here. So control plane policing, or CoPP, it allows us to prevent unnecessary traffic from oversubscribing or overutilizing the CPU. Right? We use something called the Cisco iOS modular command line configuration, or what we call MQC, modular QoS for CLI. If you've ever done any kind of QoS configurations or any kind of class-based configurations in an ASA, there are some other, MPF is a representation of this framework, the Modular Policy Framework, or C3PL, Cisco Common Classification Programming Language. But there's one thing in common with any of these configurations. We have three things that we're configuring in order to identify the important traffic and identify what's going to happen with that important traffic. So MQC uses three main configuration elements. The first thing is a class map. Now, before I can do anything to traffic, whether it's for QoS, whether it's for security policy, policy-based routing, whatever it might be, I have to classify that traffic first. A class map gives us the ability to classify traffic into a particular class. Maybe we're classifying our EIGRP packets. Maybe we're classifying our management packets. Maybe we're classifying BGP packets or whatever it might be. But in order for me to apply a policy to something, I first have to classify that information. And a class map allows me to classify the information into a particular class. When you create a class map, you use these things called match conditions to match traffic to a particular class. Maybe you're matching against an access control list. Or maybe you're matching against a protocol using NBAR. But the idea is I'm saying, okay, this traffic goes into this class, this traffic goes into this class, and so on. So we're categorizing our traffic. The next thing that happens with MQC is we set up something called a policy map. Now the policy map is what we're trying to do with that class. The policy map is in effect the action that we're taking against the traffic, whether we're policing that traffic, shaping that traffic, dropping the traffic, remarking the traffic or marking the traffic with specific QoS values, whatever it might be. So the policy map is literally what am I doing to the traffic itself. And then we have the service policy. The service policy is where I'm doing it. All right. So for example, I want to take traffic coming into an interface and I want to put that into a particular queue in a queuing system. Maybe it's low latency queuing or a class-based weighted fair queuing system. The class map allows me to identify the traffic that I want to queue. The policy map creates the queues, and then the service policy applies the policy map to a particular interface or a particular function. All right. Anybody in here ever dealt with MQC before, modular QoS or CLI? Right. It's called modular QoS here because when you think about the policing architecture, we don't necessarily want to restrict or drop traffic going to the control plane. We want to ensure that certain traffic gets more priority than other traffic. You see what I'm saying? So I want to make sure that my routing traffic gets priority, or my BGP traffic gets priority, or my EIGRP traffic gets priority. So in effect, what we're trying to do by protecting the control plane is we're trying to provide QoS for that control plane function. All right. Now I have to say MQC is a lot more than this. Obviously, we could spend 3 or 4 days talking about MQC and how it works and the different ways to classify traffic. For example, class maps have the ability to match on multiple conditions, and you can do match all or you can do match any. Policy maps, there are so many things that you can do within a policy map. Some common examples would be to police traffic or shape traffic. What's the difference between policing and shaping? Policing, we have a limit of bandwidth that's allowed for a particular queue, right? And when we're policing traffic, anything that exceeds that threshold gets dropped. Whereas in shaping, we delay traffic. We buffer traffic, we delay traffic. So shaping is a little bit less, well, totalitarian, I guess you could say. Right? It slows down traffic, but it doesn't necessarily drop the traffic. So it's not necessarily, this slide is not supposed to teach you everything you need to know about control plane policing. Remember, we're trying to introduce these concepts to give you an idea of what they are and how and that they exist, so that you can go and maybe see a little bit more about that a little bit later on. All right? Control plane protection. Now, control plane protection is a little bit different, a little bit more different than control plane policing, right? Very similar. I mean, the ultimate goal is the same, and it is to protect the control plane from denial of service attacks or, overloading the control plane with malicious traffic, all right? The thing about control plane protection, though, is it gives us a lot more granularity on the types of controls that we can employ, right? In control plane policing, you're a little bit limited because of the way you can classify traffic. We don't necessarily look at traffic flows. We're essentially classifying traffic on a per packet basis. And if the packets match the criteria, the policy gets applied to those packets. In control plane protection, we have these three predefined sub-interfaces, which are virtual interfaces to the control plane that provide certain functions. And we'll see this on the next slide, but the three sub-interfaces that exist are the host sub-interface, the transit sub-interface, and the Cisco Express Forwarding exception sub-interface. All right? Now let's talk about the first two. Just by their name, what do you think that the host or the transit sub-interface might suggest? We'll see if you're correct on the next slide. But what might the host sub-interface be used for? How about traffic going to the control plane itself? What would be an example of that? We're not talking about management traffic, but what about an EIGRP hello packet? Or a EIGRP update? Or a BGP synchronization message, right? Aren't these packets that are destined to the router itself? Those would be the host packets, right? So transit, conversely, would mean what? The traffic that gets routed, the actual traffic that passes through the device, goes up to the control plane, goes back out to the data plane, and gets sent through the device, right? And then we'll talk about Cisco Express Forwarding exceptions in a little bit, all right? So these are the different CPPR sub-interfaces that exist. Yes, it does include traffic destined to the router itself, like SSH traffic or any kind of tunneling traffic, like GRE tunneling traffic or IPsec tunneling traffic, SNMP to the router. Host in this case references specifically the router itself, the router being the host, all right? Transit traffic, as I mentioned, is any traffic that's passing through the router, right? For example, tunnel traffic passing through the router or traffic through the non-CEF interface. Well, now we have to talk about what CEF is. Anybody know what CEF is? It stands for Cisco Express Forwarding. What is it? What is the purpose of CEF in a Cisco device? Any ideas? It helps Cisco specific devices do certain things. Remember, the goal of any device, whether it's a router or a switch, is to take data into the device, process the data, and send the data out of the device. You guys agree with that, right? Otherwise, why would, I mean, if I'm just taking data into the device and I'm not sending it out, it's kind of pointless, all right? Any data that comes into a Cisco device has to be processed. Now, the ultimate goal is to ensure that we process that data as quickly as possible. We want our devices to be somewhat transparent to the data flow. Kind of like a bump on the wire, right? We don't want our data delayed inside of our device for a long time. So what Cisco Express Forwarding does is that there used to be, there are three different switching methods that a router can employ to switch traffic through the interfaces. One is process switching, where everything goes up to from the data plane to the control plane through the CPU, back down to the data plane and gets sent out. As you can imagine, that's probably the slowest method of communicating that you can use. And then we have fast switching. Fast switching is where the data goes, the first data packet in the flow goes through process switch. And then we create these caches in memory of that flow information. So the remainder of the packets that are part of that flow get switched through the data plane without ever having to go up to the control plane. Does that make sense? Yes. So the first packet is process switched. Build all of my ARP caches, my MAC address to interface mappings, my routing table map, everything, right? So that first packet gets process switched, and then the remaining packets get cache switched, right, through the data plane. Cisco Express Forwarding is essentially the same thing as fast switching, except for we proactively build the caches before a data flow comes in. So the very first packet that matches a flow gets fast switched through the router or through the device without having to go up to the control plane. So when we say traffic through non-Ceph interface, what do we mean? Traffic in which we haven't built those caches has to be process switched. And that goes up to the control plane. Remember, we're talking about, these are control plane sub-interfaces, which means that we're sending the data from the data plane up to the control plane. Yes, sir.
So the only time you don't really use CoPP is during like peak hours. I mean, because under typical usage, unless your router's being overloaded, you're never going to come close enough to all the
right. And this, you are not required to use these policing methods. In fact, most people don't use them at all. And it's not even a matter of doing it at the peak hours. The purpose of these policing methods, control plane policing and control plane protection, is to protect against actual attacks. Not just everyday processing, but somebody actually trying to overload the control plane with malicious packets. All right? So these are not techniques that you would use unless you feel like you're vulnerable to an attack at the control plane level. All right. Now, of course, as a best practice standard, Cisco says, well, you should always protect your control plane, but I would venture to say that 99.95% of the people that implement Cisco routers don't do anything with control plane policing or control plane protection, at least not in most enterprise environments, right? Certainly in more secure environments, mission critical environments where you simply cannot have any downtime, that might apply, right? So I don't want to make it seem like this is something that would become kind of a standard practice in your organization. It should be, just like any security mechanism. If I can add another level of security, another level of protection, I should, right? I mean, ultimately, that's what we should be doing. It doesn't introduce overhead. In fact, it really doesn't introduce any overhead because the whole point of this is to filter, right? We're trying to control the amount of traffic. Now, as I said before, these two slides are not going to tell you how to do all this, right? We're not trying to teach you guys in this particular lesson how to configure all of these functions, but to make you aware that they exist and what their general purpose is. That's the goal here, okay? All right, so transit interfaces, if you can imagine, come in the data plane, sent up to the control plane, back down to the data plane, and out of the device. Obviously, traffic that doesn't get Ceph switched, traffic that doesn't meet our Ceph criteria, in other words, the caches don't match the traffic flows, they're going to have to be sent up to that transit interface. All right. Now, this inbound ACL allows us to identify what's allowed to go up to that transit interface. And, by the way, we can apply rate limiting conditions. We can apply thresholds to allow certain applications to get better or more access to the control plane than other applications. Okay? The Ceph exception interface would be like if a packet has a TTL value of 1. Now, normally that packet would be fast switched through the device, but because the TTL value is 1, what's going to happen? We're going to have to destroy that packet because the time to live is going to be exceeded, which means that we now have to send that up to the control plane because there's we're not even going to forward this packet. We're going to actually kill the packet, and then we have to respond with a time to live exceeded message to the source, right? So there are certain types of packets that they would have been fast switched through Ceph, but because of certain aspects of the datagram, they're not going to be. Make sense? The Ceph compatible traffic never touches the control plane. It simply stays at the data plane layer comes in one interface. We look at all of our caches, forwarding information base, etc. We make a forwarding decision. We send it out on its way. All right. All right. What happened there? That's weird. Went right back to slide number 4. What slide are we on? That was weird. Yeah, I think I might have hit the number to go to slide number 4. My apologies. All right, let's try that again. Another way to protect access to the control plane, because remember, our routing protocols essentially utilize the control plane to process data, right? We don't Ceph switch, or we don't switch routing protocol messages through the data plane, because routing protocol messages are destined to the router itself. Agreed? I mean, a hello packet doesn't get passed through a router. Hello packets go from router to router. Updates go from router to router. They're linked local communications. So another way to protect against any type of control plane attack is to protect the protocols that use the control plane. And one of the things that you can do with that is what we call router protocol authentication. All right? It prevents the router from accepting fraudulent route updates. We already saw in a previous slide how this is actually done. We use a hashing algorithm, and we generate these hashes, which are hashed with the routing protocol message and a key, and then we send the MAC, the key ID, and the message across to the other router. So if the router receives a routing protocol message, it's going to try and verify the corresponding hash of that message to verify its authenticity. Okay? So what we do is we configure a shared secret key on the peer routers. Now, this applies to IPv4. This does not apply to IPv6. Because in IPv6, we have IPsec built into the protocol. So we can actually use true IPsec functions, cryptographic functions, anti-replay functions, message integrity functions built into IPsec. In the case of IPv4, though, this is an overlay. We're not using IPsec specifically, but we're using some security functions as part of the protocol. So we have a shared secret key that's configured on each router. The update source creates a MAC, message authentication code, using the shared secret key and the update data. What types of routing protocol messages get authenticated? Right? EIGRP has 5 message types: hello, update, query, reply, and acknowledgement. OSPF has 5 message types, right? OSPF DBD, database descriptor packet, hello packet, link state update, link state acknowledgement, link state request. So out of those packet types, which packets get authenticated? All of them. All of them get authenticated. Every single time I send a message, any message, hello, update, query, whatever, it's going to include this message authentication code, and then the receiver verifies the MAC using the shared secret key and the data that it received from the sending router. The protection of the routing protocol, remember, we're not trying to protect the confidentiality of the data. The data doesn't have to be confidential. The updates, the replies, the queries, they're all sent in plain text. We're simply trying to authenticate the source of information, number one. And secondly, we're trying to verify the integrity of the data that's being received. So somebody's not modifying the hello packet midstream, or somebody's not modifying the EIGRP update midstream. Okay? So this provides integrity, but no secrecy. The protection is only as good as our secret key as well. Somebody could use a brute force attack to discover our secret key because they're getting the plain text message, right? The concept of breaking a cryptographic system is called cryptanalysis. And there is a a way, there are multiple ways that we can break different algorithms and different security functions. But if I know the plain text and I know the hash, can't I start using rainbow tables or some sort of brute force method to try and figure out what the secret key is? Right? Because all I'm trying to do is generate the same hash. So that being said, make sure that the passwords are still secure passwords. Don't use Cisco as your shared secret key, because somebody can use a brute force attack to get that secret key. All right. So it's very simple the way it works. I've got a router on the left. The router on the left is talking to the router on the right. We'll just put a little router there and a little router there. And so I've got a routing update that I want to send, whether it's EIGRP or OSPF or RIP or whatever. And then I have the secret key that was configured on both routers during the configuration of the routing process. That goes into my hashing algorithm, MD5 or SHA, and out comes the message authentication code. Looks pretty similar to something else, doesn't it? In fact, it's the exact same diagram. The only difference is instead of saying routing update, we said NTP update, because just about every protocol that utilizes hashing for authentication and integrity uses this same process. So the MAC gets sent with a routing update. The routing update gets received. We take our secret key, we run it through our hashing process, we generate our own MAC, and if it matches the original MAC that was sent, then we've authenticated the update and we've authenticated the source of information. Because again, the only way that the source of information would be known, or the source would know is secure, would be to have the same secret key. All right. The way that we set up router authentication is we have to specify our key chain. It's a little bit more complicated than this, but again, we're really just trying to introduce these concepts. In the CCNP routing and switching course, we get into routing protocol authentication in a lot of detail. But so we're creating a key chain. In this case, it's called OSPF keys. And then each key has something called a key ID. So this is key number 1. You can actually have multiple keys in the key chain. Those keys can even have a lifetime. When we set up routing protocol authentication for our customers, we usually have at least 12 keys in our key chain. And we rotate the keys once a month. Right? And then at the end of the year, we go back and we say, okay, we need to set up your authentication again. Because once the keys expired, the routers don't work anymore. They don't talk to each other anymore. Which is something you have to pay attention to, of course. But we don't use the same static key over and over again. If we do, in some cases, customers don't want to have to deal with keys changing every month. So if we do use a static key, we make sure that it's a very, very long, very, very secure key. Make the key space really, really large so that even if somebody's doing a brute force attack, they wouldn't be able to discover that key in any lifetime, right? So the key string is literally the key itself, all right? The key string is the key itself. Don't use Cisco, use something that's secure. The key ID, which is key 1, and the key string have to match on both sides of the routers. What does not have to match is the actual keychain name. Keychain name is local to the router. We don't send the keychain name along with the routing information. We do, however, send the key ID. I don't know if you guys remember in the OSPF packet header, there were fields in the OSPF packet header for authentication, okay, which includes identifying the authentication type and the key ID. Not the key chain, though. We don't, not the key chain, not the key string. Obviously, it would be stupid to send the key string in with the routing protocol message. In this case, we're going to use SHA-256 HMAC. So we're using a 256-bit hashing process, right? And I don't know if you guys are familiar, but we'll talk about this in the next chapter when we get into cryptography. But hashing processes take a variable linked input message block and they generate a fixed output message block. So the output string, the message authentication code that's going to be generated from this hashing process, will be a 256-bit hash. SHA-1 generates a 160-bit hash. MD5 generates a 128-bit hash, okay, from a variable length input. The HMAC component, as we mentioned before, if it was just SHA without HMAC, that means there's no secret sauce. There's no key involved. But the HMAC component means that we have this key string component involved as well, which protects against man-in-the-middle attacks. All right. So we set up our key. We go into the interface to which, or from which we're sending OSPF messages and where we're going to be receiving OSPF messages, and we simply apply the keychain to the interface. Very simple. Duplicate that configuration on the other router on the other side of that interface, and you now have routing protocol authentication configured. Pretty simple. Not that complicated. It's a little bit different in EIGRP. The process in EIGRP is configured a little bit differently. Older versions of EIGRP, you could only do MD5 hashing. In OSPF, you can do MD5 and SHA, and you can do plain text, which obviously would be kind of pointless because the key is actually sent in with the hash. There's some other implementation options. You can enable OSPF authentication in the routing process, or you can enable it on the interface, and there's some other aspects that you can configure as well. All right. EIGRP router authentication. Again, we create a key chain with a key ID and a key string. And then we specify on the interface that we're going to run authentication. Never understood this command because the only authentication you can run in EIGRP is MD5, but they still require you to specify the mode. If you were to go IP authentication mode, EIGRP, EIGRP 10 is the autonomous system number. All right. But if you were to do this command with a question mark, the only option you would have is MD5. Never understood that. All right. Only option you have is MD5. So you can't run SHA. Maybe in the future releases of EIGRP, they'll add additional options. But as far as I've seen, with the latest version of code, MD5 is the only option. Okay? And then we apply the key to the interface. So this routing protocol authentication is done on a per interface basis, meaning that you can run authentication with some neighbors, but you don't have to run authentication with other neighbors. Does that make sense?
Yeah. Keychain.
Yes, sir.
Taking it from your website. Is there more than one key potentially in the keychain?
Yes. You can have multiple keys within the keychain.
Right. So if I've applied that more generic looking, I don't specify a key ID at the interface level.
No, in either case, you don't specify a key ID. We didn't. Well, what happens is we look at the list of keys, and we use the first available key in the list. All right? So let's say I have a keychain of 5 different keys. Now, the purpose of having multiple keys in the keychain is to say, okay, this key is valid from this period to this period. Once this key expires, then the next key is valid, and so on. So the router's going to pick a key ID with a key string from the list based on the first available key.
So there's obviously no parameters to the key.
Yes. There's key lifetimes and so on. Right.
Keys by way of that.
Right, by specifying key lifetimes. Yes, another important reason for NTP to be in sync, because your key lifetime, if I send the OSPF update with key 1, you need to be able to verify that update with key 1. And if your time is different and your key is expired, then you can't verify the update, and routing process fails at that point. You can overlap keys. In fact, you would want to overlap keys in case there's some variances in time. Now you don't overlap by weeks or months.
Yeah, but it processes it from the top down.
Yes.
It's signed when it's still within the lifetime, but continue to try to use it.
Yes, that's correct.
And that's why you get that.
Right. And so if the clocks are not completely synchronized, maybe by hours or minutes, if you have overlapping keys, there's really no potential of having a failed process because the key's expired when it's not supposed to be. Right. Well, yeah. I mean, literally the lifetime of the keys are based on the show clock output, whatever that clock says. All right. All right. All right. That was an easy chapter.